So we're going to talk about these sort of C4 BandPass filter circuits. And the first part is, of course, going to be talking about what does the circuit look like in the FPA structure itself. The second thing, though, is also talking about abstraction. Most people tend to think that you don't get abstraction in analog circuits, and I think this structure kind of lends us to a point of saying maybe there's something else going on here. Okay, so we want to start to think about these various parts and blocks and so forth. So one of the things you see is that we'll have this sort of C4 block, and most people will typically come to seeing this as what is a simple block of I have a vectorized inputs, I have vectorized outputs, and I have a single reference point voltage for all of those filters. Vectorized very commonly on the output because we often want several. Sometimes we only want one input, and that gets shared among a bunch of the devices. Very typical structure, a lot of different ways you could imagine doing this. And so you look at this block and you go, yay, great. It's a nice simple block. I put it down, I double click on it, there's a couple parameters. Some make more sense than others. But for the most part I can just kind of proceed, right? Because I have to look for a couple corner frequencies, I'm good. Well, when you look at the circuit, it's basically two floating gate OTAs. And you think, okay, that seems reasonable. And then basically one capacitor, and there's some parasitic capacitance around the edge as well. Okay, so this all seems to work pretty well. And then you start to go, well, then you ask the question, well, what is in a floating gate OTA? Because there's a whole bunch of biases, and I need to understand what am I doing with these biases. Okay, so then I say, well, I have a floating gate OTA, and this is sort of, and I can kind of get into sort of its level 2 kind of description now, because I need the voltage and current. Level 2 means I need to deal with the current voltage relationships versus level 1, which is the more data flow form, which is the more voltage in, voltage out, the more abstractable case. But we need to understand what's going on in here. And so this block basically is an OTA with floating gate elements on the minus and plus terminals. These floating gate elements they're selectable. You have a few options actually, because we actually allowed for a few selectable options there. So a couple different size coupling capacitors, and the rest goes to ground. Allows me to do a couple of things. Allows me to choose what is the linear range of the OTA. Now we don't know. Well, we've got to figure out what the OTA is, but we'll get to that in a moment. It allows me to choose the linear range. It also allows me to choose the offset. So I can choose the various voltage offsets on here as well by basically programming the floating gate charge here. The floating gate charge, by the way, is in terms of often referenced in terms of its currents from the PFETs, both in negative and positive current. That's not an NFET or PFET current, it's in negative and positive currents. That this is sort of a traditional way of referring to it. So if you actually see a current N and current P on there, that's probably the positive and negative currents for effectively these two OTAs. Right? One of which is going to be the feed forward and one is the feedback structure. And you think, okay, that turns out to be very useful. I have a number of parameters in there and selectable capacitors. In fact, I can imagine selectable capacitors because even this capacitor I have multiple different options. And the way it is set up is a set of capacitors with a number of switches in it that allow me to keep those capacitors in the actual circuit itself. This turns out to be extremely useful because now I can choose how much coupling do I want into it, or do I want to make it smaller. Typically you'll see this will be a fairly large number. You're actually allowed to change that coupling strength. That's typically one of the parameters in the C4 block itself. So you think, alright, I got a full understanding now, except that, okay, an OTA, well, this could be voltage in and current out, but are there anything else I need to know? Well, when I look at this structure, it is basically a 9-transistor OTA, classical PFET diff pair, NFET current mirrors, PFET current mirrors, no cascodes on it, because typically we're not doing a lot of high gain stuff in most of these FPA structures anyways. Often because we have precision because of the floating gates itself, so we're not needing it for other reasons, so typically this is sufficient. And so then on top of it, then we have another floating gate here, which is the bias current, and that bias current is extremely important because that bias current, coupled with all of the capacitances at these nodes, or the effective capacitance of this node, sets the time constant. And there's two time constants. You have two floating gate elements, and those time constants will be affected accordingly. Both of the OTAs are floating gate OTAs, which actually have its own parameter. So when you look at this circuit at a very simple level, it's very easy to imagine having 6, maybe 7 parameters right off the bat for this what seems like very innocuous looking little bandpass filter. And those could be abstracted, those could be very explicitly given to you. Okay, so there's a couple different ways the modeling could be done. But it's kind of important to know that you've got quite an amount of flexibility on what is already, what seems like a very nice, simple little innocuous block to work with. And what I want you to have an appreciation of is just be able to use the block, and this is really awesome and it works well, but also know what's underneath it when you need it. Either if you're trying to program parameters, or if you're trying to figure out how to utilize various features and various concepts at different places.